Okay, let's talk about two-dimensional forces. We know that the forces add up to zero. This object's at rest. The fact that the object's at rest and constant velocity tells me that the sum of the forces have to add up to zero. So that now I could have constant velocity and be moving. Remember, cruise control is an example of that. So let's take a look at this sign problem. Now, the things I'm going to try and find on the sign problem is I want to find the tension in this cable. Now I'm going to label the tension as T. I'm going to call that TR because it's in the right direction. I will call this TL because it's in the X direction. My goal is to find out what is the force in each one of those cables. Now, if you go back to your studies of math, in order to have two unknowns, you're going to have two equations. Well, the two equations are going to come from this fact. The fact that the sum of the forces add up to zero. What I can say is the sum of the forces in the X direction have to add up to zero. It's not accelerating in the X direction. And also the sum of the forces in the Y direction have to equal zero. So I'm going to use those two facts to help me solve it. Now, first thing I do with any problem like this is I draw a free body diagram. Anytime we're dealing with forces, we want to draw a free body diagram. So let's label the forces acting on that object. I'll pull it down where you can see it. Of course, we know that we have weight going down. Notice I'm not putting numbers on it. I'm just putting all symbols. Then I'll do it later. Then over here, I have TR going in that direction. And then over pulling from this side, I have TL. Now, the direction of the arrow is important. If I was to cut this, the force is acting in that direction to keep it moving. To keep it from moving. The same thing is the force has got to be pulling up on it there to keep it in place. Now, that's my complete free body diagram. If you're being graded on the free body diagram, that's all you need. Now, to solve it, you need to, though, add a little bit more to it. So what I'm going to do now is underneath this, to help me solve it, I'm going to draw a pseudo free body diagram. What a pseudo free body diagram is a diagram that's going to help it make this easier to solve. Now, I still have my box. I still have FG. I'm not going to put that it's coming from the Earth. You already know that. I still have TL. And I still have TR. But now what I need to do is I need to shift it based on my coordinate system. So I need to get everything in either the X direction or the Y direction. And right now I have one that's got parts of both. So what we would do is we do this. And that's the reason we've been talking about components. This is going to be TRX. This is going to be TRY. If you put those two together, you get TR. So really what I can do now is I can essentially, let's even do this. I can actually, at this point in time, get rid of this TR. Because what I've done is I've replaced that initial TR with the TRX and the TRY. Now, in order to solve it, let's come down here and let's create an XY chart. Now, an XY chart, you have X and you have Y. That's called an XY chart. Now, what I'm going to do is take all of three of my vectors and I'm going to put them into their X part and their Y parts. Now, the three vectors I have, doesn't matter which order you do it in. I have TL, I have TR, and I have FG. Those are the three vectors. Now, the important things to understand is this column has to add up to zero. Because what we're really going to do is sum up these forces, and they have to add up to zero because the object is at constant velocity. This side also has to add up to zero. It's not accelerating in any direction. So now, what we're going to do is we're going to do it. Now, TL. Now, if you look at TL, TL is pointing all in the negative X direction. That's an X. It's pointing all in the negative X direction. So what I'm going to do here is put negative TL. I don't know what that is, so I can't do anything. But here's the nice thing. None of it's pointing in the Y direction. It's all perfect, pointing perfectly that way. Now, TR is the only one that gets complicated. TRX. Now, I'm going to write it as TRX. In a second, we'll figure out what it is. This side would be TRY. FG is what's acting straight down. Now, down is in a negative y direction, but I know what number this is. Remember, it was 50 kilograms, so therefore this is 500 newtons. So acting down, I have nothing acting in the x direction, and I have a negative 500 newtons. Again, negative because it's acting down. I said up was positive. So you get to choose that. Now let's go up to this one and expand it a little bit. What this is going to be is TR. Well, it's that side of the triangle which would be the adjacent, so it's cosine. So TR cosine of 30 degrees. Sorry, I needed to write that a little bit bigger. This one is going to be TR sine of 30 degrees. Now, once I get that, I really don't need this. That was just to kind of help me. Now, here's the thing. Sines and cosines are numbers you know. So if I take a look at this side here, that plus that have to equal 0. That plus that have to equal 0. So I'm going to do this side first, because this side only has one unknown. So I'm going to say the sum of the forces in the y direction equals 0. Now, the sum of the forces in the y direction, well, I have TR. Well, the sine of 30 is 0.5. Your calculator knows that. Minus 500 newtons is equal to 0. So I get TR times 0.5 is equal to 500 newtons when I move it to the other side. So therefore I get TR is equal to 500 newtons divided by 0.5. So TR is 1,000 newtons. Now, at that point in time, I've solved for TR. Now I want to solve for TL. In order to solve for TL, I got to go one more step. I'll try and do it where you can still see it. What I'm going to do now is I'm going to say the sum of the forces in the x direction have to add up to 0. Well, the sum of the forces in the x direction are negative TL, which I don't know. Let's do it all in terms of things first, in terms of just variables, plus TR times the cosine of 30, and that's all going to be equal to 0. Now, let's put in TL. I still don't know. I do know what TR is, though. It's 1,000 newtons. That should be a plus. 1,000 newtons. The cosine of 30, again, your calculator knows it, is 0.866. I don't expect you to know that. Your calculator knows it. That has to add up to 0. So I get negative TL plus 866 newtons is equal to 0. And of course, it's pretty easy then to see that TL is going to equal 866 newtons. You've now solved both of them. The key thing with a sine problem is that your constant velocity, it can be moving, but it cannot be accelerating. So therefore, we know the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. Now, you could, we won't do it in this class, but in the future, if you studied this in greater detail, you could actually make three-dimensional structures, and you could have a sum of the forces in the z direction equal to 0. So you could add another layer of complexity to it. Physics problems don't necessarily get any more complicated as you go up the ladder. Well, I guess I should say that different. They don't get any more complicated from a physics point of view, but they can become more complicated from an algebraic point of view. But the physics still really doesn't change. You have an object here at constant velocity. If it's at constant velocity, the forces have to add up to 0. Now here's the thing that takes a little bit of thinking. You have 1,000 newtons acting to the right, you have 866 newtons acting to the left, and you have 500 newtons acting down. But when you add all of those up, the sum of the forces total is equal to 0. That's because we're talking about an object that's not accelerating. Later on, we'll talk about objects that are accelerating, and then it adds another little bit to it. But right now, they're not. Hope this helped.